And then we're just gonna quote a result from thermophysics, from statistical physics. I can't remember, have you had that yet? Or, yeah, you haven't yet. So stay tuned and you'll see more of this then. But here you'll just take my word for it, and it's kind of believable stuff. So I'll just read it first and then we'll write it down. In thermodynamic equilibrium, then statistical mechanics shows that the ratio of the probabilities P of S sub B and P of S sub A of finding the system in one of the two states is given by, and then I'll write the equation that says what it's given by. And another way to put it is that the fraction of the atoms in state SB and the fraction of the atoms in state SA has a certain ratio, and there's a famous formula that gives that ratio, and it comes from statistical mechanics considerations. Actually, it's when they're in that ratio, you maximize the entropy, and that is the condition for thermodynamic equilibrium. Nothing is changing over time on average. Just as many atoms go from state A into other states as are at the same time going from other states into state A, so that the fraction of the atoms in state A stays constant with time, except for little statistical fluctuations. So, more on that later when you take another course. But for now.
Next spring.
Yes, something to look forward to. Then in thermodynamic equilibrium, statistical mechanics shows that the ratio of the probabilities we'll call it P of S sub A and big P of S sub B, that a given atom is in one of those two states is given by P of S sub B divided by P of S sub A is equal to e to the minus e sub b over kt divided by e to the minus e sub a divided by kt. So remember that kt has units of energy. It's a characteristic thermal energy. So this is e to the minus energy of the state over the characteristic thermal energy. And what we're learning is that, in fact, the probability of finding the atom in a given state is proportional to e to the minus energy of the state over the thermal energy. So the more energetic the state, the less likely you are to find the atom in that state. Physically, that's because to get an atom into an excited state takes like collisions and things like that. And the higher the energy is, the lower the fraction of the atoms that will have enough energy to have a collision cause a transition into that state. And of course, using the laws of exponentials, you can also write this as e to the power of minus e sub b minus e sub a over kt. So in other words, the ratio of the probabilities is determined by how different the energies are compared to kt, exponentially. So what this is saying is, as the energy difference grows, the probability of seeing it in the upper state compared to the lower state decreases exponentially. If you double EB minus EA, that does a lot more than cut the probability in half because of this exponential there. And a term of this form is called a Boltzmann factor. And we're not at the Boltzmann equation yet, but we're on our way. So let me write that out.
Oh,
This is not the Boltzmann equation yet, I know, yeah. Because what we still need to account for, what we actually want in the Boltzmann equation is the probability ratio in terms of energy.
okay.
And
so we need to
account for degeneracy.
Oh, yes.
There are more ways to put the electron in the n equals 2 level than the n equals 1 level, because the n equals 2 level has more available values of the other quantum numbers.
Yeah.
And so that plays a role as well.
It's the p orbital, right?
Yeah, because there's two, n equals 2 has both s and p.
Yeah, so it's
L equals 0 and L equals 1. And each of those has different numbers of m sub l available to it. And so we'll go through all that. But I should here write that a term of the form e to the minus energy over kt is called a Boltzmann factor. After Ludwig Boltzmann. Oh, and I'll also remind that K is 8.62 times 10 to the minus 5th power EV per Kelvin. So it's useful to put it in EV because we're often dealing with EVs as energies on an atomic scale, is the Boltzmann constant. So notice when you multiply by the temperature in Kelvin, units wise, the Kelvins cancel out and you're left with an energy V.
I see, and that's a term energy with the, what is the capital E in the equation defined as kinetic plus potential?
It's the, so the E would be, for example, the energies of the state. So we usually reference it to 0 and infinity. So in other words, to the ground state, E would be minus 13.6 electron volts. For the first excited state, it would be minus 3.4 electron volts, and so forth. That would be plugged in there. It wouldn't matter. You could also use these values as well, because notice that when you take the ratio, EV minus EA, it's not going to matter where you put the 0 point. Where you reference them to. The energy of this state minus the energy of this state is 10.2 electron volts, whether you call this one 0 and this one 10.2, or whether you call this one minus 13.6 and this one minus 3.4. So from that standpoint, it doesn't matter. Yeah.
Because the difference is still
It's the difference that matters for finding that ratio as what shows up. Yep. All right, we should take our break at this point.